Gym lectures. In this series, we're looking at the topic atomic structure and electronic configuration. Without further ado, let's dig in. Before understanding the atomic structure and electronic configuration, it's cardinal to understand the Bohr model of the atom, the historical aspect of the atom. So, the first ever discovered model describing the arrangement of the atom was the Bohr model. In science, the Bohr model was discredited due to its incompetence in the occupation of electrons. So it was discovered to say some subshells or energy levels are able to occupy a number more than 8 electrons, of which the Bohr model suggested the maximum or the octet number to be occupied by these shells was 8. So this was one of the limitations of the Bohr model. Hence, the Bohr model has been discredited and is not used. So the introduction of subshells discredited this model. So we don't apply this model in science, we apply the updated model which includes subshells. Subshells include the S subshell, the P subshell, the D subshell, and F subshell, of which these subshells have orbitals, and these orbitals are able to occupy these electrons respectively. So, without further ado, we designate each subshell with the total number of electrons it can occupy in its orbitals. So for the S orbital, the maximum number of electrons to be occupied is 2. For the P orbital, it can occupy a maximum of 6 electrons. The D orbital can occupy a maximum of 10 electrons. And finally, the F orbital can occupy a maximum of 14 electrons. So with this being said and understood, we can incorporate the aspect of orbitals in our understanding of atomic structure. Okay, below here is a section containing the constituents of an atomic nuclei. So atomic nuclei constitutes of neutrons, protons, which are positively charged. Protons are given by a quantity we refer to as atomic number. So atomic number or proton number constitutes of the total number of protons. Mass number is a quantity that constitutes of the total number of protons and the total number of neutrons. So the sum of protons and neutrons equals the mass number. Hence, given the mass number and the neutron number, we're able to deduce the proton number. Mathematically, we're able to utilize this principle in understanding the total number of protons or neutrons, provided we have the mass number. Okay, so below here is a statement saying protons, total number of protons is equal to total number of electrons. This suggests that the total number of protons, which is the atomic number, is in fact the total number of electrons in this atom. Hence, given the atomic number, we're able to deduce the total number of electrons. So let's keep these principles in our understanding as we go deep in electronic configuration, for these will be the bricks we use to build this house of understanding. When deducing the electronic configuration, it's cardinal to take into consideration the total number of electrons present in this atom. So the total number of electrons can be deduced by the atomic number. So atomic number is equal to the electrons in the atom. Hence, the distribution of electrons depends on 3 major guiding principles, and these principles help us understand the criteria we use in filling these electrons in their various subshells and orbitals. These rules consist of Aufbau's principle, which states electrons occupy atomic orbitals from lowest energy level to higher energy levels. This principle states that these electrons will move from low energy regions to higher energy regions in occupation. This principle therefore suggests a higher energy orbital can't be filled before a lower energy orbital. Pauli's exclusion principle, which is our second principle, suggests atomic orbitals can occupy a maximum of 2 electrons, each which are of opposite spin. So the maximum of electrons to be occupied by an atomic orbital is 2, and of which have to be of opposite spin. So if one has a positive spin, the other one has to have a negative spin. Hard's rule, which is our third rule, Hard's rule suggests if an atom has more than one orbital of the same energy level, electrons tend to distribute singly among the orbitals before they can pair up in one. So that means electrons distribute singly in each orbital. If we have an atom that constitutes of orbitals of the same energy level, each orbital will have a single electron before any orbital is paired with 2 electrons. I'll demonstrate this in a p orbital, where I'll have to fill this p orbital with a maximum of 6 electrons. And I'll demonstrate the filling of these 6 electrons with respect to Hard's rule. Follow me through my demonstration as I fill these orbitals. One electron, another electron, another electron. That's 3 electrons. So we have 3 more electrons remaining to be filled in these atomic orbitals. This is an illustration of how we can obey Hard's rule, which states atomic orbitals of the same energy level are filled singly before being paired doubly in one orbital. So the rest of the remaining electrons, which are 3, are going to start pairing up in each orbital, seeing to it that each and every individual orbital in this energy level has been singly filled. So we expect pairing to occur. So 1, 2, 3. This marks our understanding of the guiding principles of electronic configuration. Without further ado, let's look at an application of these principles on actual atoms given their atomic number. Let us proceed with a practical illustration of an atom and its atomic number. So in front of me is a representation of sodium atom, which has an atomic number of 11. Atomic number of 11 suggests that this atom has a total number of 11 electrons. And electrons are the principle we use in deducing electronic configuration. So we will therefore start by filling these 11 electrons into the various orbitals. We will respect first and foremost Aufbau's principle by starting from the lowest energy level in filling these electrons, going to higher energy levels. That's the first principle that we have to observe. And as I'm filling these these orbitals, we'll be able to understand and apply the various guiding principles behind the electronic configuration. So without further ado, I'll begin. A total number of 11 electrons are present in an atom of sodium. So these electrons are going to be filled in these various orbitals. So the first orbital to be filled is the 1s orbital, where we fill with one pole, and we fill with an opposite pole, respecting Pauli's exclusion principle, which says an orbital can occupy a maximum of 2 electrons, which have to be of opposite poles. So by this we've applied Pauli's exclusion and Aufbau's principle. So we'll do the same for the 2s orbital. keeping in mind the total number of electrons is 11. So, so far we have 4 electrons. That means we are left with 7 electrons to fill our complete sodium atom and come up with our electron configuration using the Aufbau's model. So, in the 2p orbital, I will singly fill each orbital with a single electron before I can pair an orbital with 2 electrons. So, 1, 2, 3, 4, 5, 6. Okay? So that's giving us a total number of 10 electrons, which means we're remaining with 1 electron to satisfy sodium's electronic configuration. So this 1 electron is going to occupy the s orbital, 3s orbital. Therefore, this is our electronic configuration, and we can deduce this and write it in notation form as 1s2, 2s2, 2p6, 3s1. Therefore, ladies and gentlemen, this is the electronic configuration of the molecule or the atom sodium. So, this is atom sodium as electronic configuration based on the Aufbau's model, and we're able to deduce various properties of sodium from this information. So, from this information, we can now utilize what we're calling the outermost configuration. The outermost shell configuration is going to help us elucidate various properties of this atom. So the outermost shell configuration depends upon the highest energy levels. So when we observe an electronic configuration, the highest energy levels are seen to be 3s. 3s is seen to be the highest energy level. So this will appear on our outermost shell configuration, 3s1. So from this outer shell configuration, we're able to deduce certain information such as the period of the atom, the group of the atom, the reactivity of the atom. So the 3s1 is showing us that this atom is in group 1. So the exponent can show the group. So the exponent of the molecule is showing us the group of the molecule. And therefore we can conclude to say sodium belongs to group 1. So the group is group 1. The period. So we can also use this outer shell configuration to come up with the period of the molecule. So therefore, the coefficient of the subshell is the period. So the highest coefficient present in the electronic configuration is always the period. So in this case, the highest coefficient is 3. Therefore, for this molecule, the period is 3. So sodium is in group 1 and appears in the period 3 of the periodic table. So we're able to locate this molecule on the periodic table from the information of the atomic number. These principles help us constitute the electronic configuration and appreciate the role it plays in understanding the atomic basis of atoms. Let us proceed by looking at another molecule, other atom that we look at, which will try to deduce its electronic configuration, its group and period, will be manganese. Manganese has an atomic number of 25. That suggests that manganese has a total number of 25 electrons. So manganese has 25 electrons in its orbitals. So let's fill these 25 electrons starting from the lowest energy respectively to higher energies. Okay, So follow through as I fill these atomic orbitals starting from lowest energy orbitals. So let's take count of electrons as we move. Alright, so the above depicted illustration is showing the electronic configuration of manganese. So manganese has 25 electrons, and the final orbital to be occupied by manganese is the d orbital, which has a maximum of 5 electrons. Okay, so let's try to put this in notation form, and the following is a notation form of manganese electronic configuration. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 3d5. Okay, so this is therefore, ladies and gentlemen, the electronic configuration of manganese. So from this now, we are able to deduce the outermost shell configuration. The outermost shell configuration will help us by giving us sustainable information that will show us the group and the period where this atom belongs. So let's identify the outermost shell configuration from this electronic configuration. Okay. So the outermost shell configuration will be the highest energy, which is the 4s2. Okay. So this molecule has peculiar properties because the highest energy that is present in this molecule is filled, but we have an orbital which has molecules or electrons that are half filled, which is the d orbital. So elements that have a partially filled d orbital are considered to be transitional metals because they have a d orbital that is partially filled, and electrons are able to migrate from the s orbital into the d orbital, causing them to have a property we call variable valencies. So this property of having a partially filled d orbital suggests automatically that this atom belongs to the group we're calling transition metals. Alright, having said that, we are able to deduce the period of this atom, manganese, and the period is always deduced by the highest coefficient to the subshell. So from this electronic configuration, we can attest to say the highest coefficient is the 4. So 4 is therefore the period of sodium or manganese. Right? Pardon me. So this information has suggested that manganese is a transition metal and is in the 4th period of the periodic table. So let us therefore look at another molecule from another group and let's identify properties of this molecule. Our final molecule we'll look at will be oxygen of atomic number 8. So oxygen of atomic number 8, with this information of the atomic number, I expect you to come up with the outermost shell configuration, the group, the period, and the electron configuration in notation form. If there are any questions on anything that was presented, please help us by putting your questions in the comment section. I'll be able to address these questions in the next meeting. Thank you very much for watching. Please like and subscribe. Watch our page, share us, and we'll be able to create more amazing content for you and your loved ones to enjoy the wonderful chemistry.